Hello, everyone. Welcome to this presentation on exploring Hasura as a data access layer in distributed systems. My name is Himshwet Gaurav. I'm the founder and senior product engineer at Krafteer. It is a digital product studio in Tallinn, Estonia. Over the last 2 years, I was building a CRM solution using Hasura. In this talk, I'll share what I have learned about using Hasura in a serverless and event-driven architecture. Now, the title of the presentation sounds too enterprising. So what are we exactly going to talk about? Almost all of us have at some point built the simple three-tier system with a presentation layer, business logic layer, and data layer. It serves well for a moderate load. However, as the number of developers working on the product increases, or the load on the system increases, or the code base increases to implement features after features, the system grows in complexity and evolves into some variant of a distributed system. On one end of this complexity spectrum is our nice little three-tier architecture. And on the other end, we have this beast with over thousands of microservices, something that the likes of Netflix use to cater to their 100 million plus customers. This jump in complexity does not happen overnight. We gradually break the monolith structure and start extracting microservices out of it. If you're someone who is on this journey and is looking for the next step from the three-tier system, then this talk is for you. In the first section, we'll discuss the specific challenges of building a serverless architecture using AWS Lambda and how Hasura can help us resolve those issues. And in the second section, I'll brief on the event-driven architecture and share a configuration that we developed and deployed in production using Hasura. So, what is serverless architecture? Serverless is marketing speak and a misnomer. We have code, and to run this code, we definitely need a server. It is just that we don't need to manage it. Essentially, we write our code, and to execute this code, we need a machine with the necessary runtime. So we package our code and hand it over to our serverless or function as a service provider. We tell them when and how to run it, and then our provider manages the runtime, which is basically a container for our code, and it executes it as and when required. Now, the two key operating words here are managed and stateless. These two keywords are the source of all the pleasure and pain of serverless architecture. Managed sounds great until you realize it is also loss of control. We have no control over the lifecycle of the container in which our code is being executed. And stateless, which means there is no shared execution context between two copies of the code running on separate containers. Now, this gives us the freedom to run 1,000 copies of the code concurrently without any worries until your functions need to access the database. Now, in the good old system where you had multiple processes, each process would pick a connection from the pool to reach the database. If you had more processes than the connections in the pool, the process would have to wait its turn. But when we go into the serverless architecture, there is no shared context. There is no straightforward way to have a connection pool. So if you have 1,000 Lambda functions running in parallel, each function attempts to connect to the database separately. And why is that bad? You might have a database that only supports 200 connections. Now, even though you have 1,000 Lambda functions executing in parallel, there is only the chosen 200 that can complete their tasks. What about the other 800? Well, the best case scenario, they wait long enough to get the connection, or they throw a timeout error. If you have configured your Lambda for retry, this cycle repeats. The other reason why it's not a good idea to sacrifice connection pooling, each connection you make to the database takes up resources. So if you have 1,000 Lambda connections running each with its own connection, you might starve the database of resources. By the way, for the folks who need connection pooling for their Lambdas now, AWS has recently launched something called RDS Proxy. Last I checked, it was still in preview, but you might want to explore that. Next, I'm going to talk about a couple of issues specific to AWS. This is when the Lambda function in AWS needs to connect to a relational database instance. So AWS provisions RDS inside a virtual private cloud. For your Lambda functions to have access to your RDS, they must also be deployed inside the virtual private cloud. This creates two challenges. First, a Lambda function has a cold start of anywhere between 1 to 5 seconds. Now, when you put the Lambda function inside a VPC, it needs what is called a elastic network interface. Think of it as a virtual network card. Now, this assignment of ENI can increase a Lambda's cold start to more than 10 seconds, which severely erodes the user experience. Second, if you have the Lambda inside a VPC, it can no longer access the resources on the internet. You basically have to provision a NAT gateway or some kind of service endpoints for this, and that is going to cost you more. Last year, I think late last year, AWS announced it is mitigating these issues by using AWS Hyperplane. I haven't used it, but it is worth exploring. Now, we were facing few other challenges as well. Integrating the Lambdas with the Cognito, which is AWS managed authentication service, was also very difficult. We also hit the Lambda zip file size limits. Those node module folders don't help. So essentially, by the time we completed our prototype, I had 99 problems, but as advertised, managing server wasn't one. So at the end of the prototype stage, we were left with these 4 key issues. The first 2 related to AWS and Lambda. There was no database connection pooling. There was high latency for the Lambda functions. And to give them internet access, we had to spend more money. In addition, we had 2 other issues. This was due to our deeply nested GraphQL schema. So our SQL queries ended up being very complex and almost unmaintainable at that point. And we had multiple n+1 query issues in our GraphQL resolvers. We started looking for solutions and we explored, among others, Hasura, Prisma, Data Loader, PostgreFiles, and few more. In the end, we chose to go with Hasura, as it solved all of our 4 key problems. And this is how we re-architected the application. So first and foremost, we moved all the Lambdas out of the VPC. Now this solved the internet access and cold start issues. Next, we placed Hasura inside the VPC, the virtual private cloud, before our RDS, the Postgres database. And we opened a public port for Lambdas to access Hasura. So now the Lambdas no longer opened connections to database directly. They made requests via Hasura. In this design, Hasura managed the database connection pool. And since we were now accessing database using GraphQL instead of SQL, we could throw away all our unmaintainable SQL queries, and we no longer had to deal with any of the n+1 query issues either. So by using Hasura, we were able to resolve all the 4 key issues that we had with our system. From this experience, I have learned 2 very important things. I hope I haven't given you the impression that I hate serverless or Lambda functions. I learned that they fit a use case particularly suitable for stateless job processing. And my mistake was to use them in an application with heavy state requirements. I have also now started to see the word managed very differently. A managed service makes certain trade-offs on your behalf. And if those trade-offs align with your requirements, it's all sunshine and rainbows. But if they don't, it's an invitation into a world of pain. So while choosing any new technologies, and Hasura included, please do your due diligence in what trade-offs that technology has made for you, and if they align with your use case and your requirements or not. Secondly, this was the first time I was accessing a SQL database using GraphQL. Initially, I was skeptical, but now Hasura is my go-to tool for accessing Postgres. Querying data via GraphQL is very intuitive, especially if you're dealing with multiple joins and you have multiple one-to-one and one-to-many relationships in your tables. And especially in these scenarios, the productivity gains are massive. And knowing that I always have the option to execute raw SQL makes using Hasura a no-brainer for me. All right, now let's move on to the second section, the event-driven architecture. So what exactly is an event-driven architecture? Let's take an example of an application which is using microservices. Now, here you can see we have these 4 services: order, user, payment, and shipping. Now, when our customer places an order, a typical order flow would involve a request to the order microservice. The order microservice creates a new order record. It then makes a series of requests. First, to the payment service to charge the customer's card. Once the payment is successful, it requests the shipping service to make a shipping label. And finally, it requests the user service to update the customer loyalty points. Now, once all these requests are completed, the order service sends a success response to the customer. Now, it's a fairly simple design, nothing complicated about it, and it gets the job done. And we can also have some separation of teams, each working on these services. However, this design leads to the following challenges. First and foremost, if any of the user, payment, or shipping services goes down, no orders can be processed. So each service introduces a single point of failure for the entire system. Also, the response latency of the order service is determined by the slowest response. For example, if the payment service takes 5 seconds to process the payment, the order service will take more than 5 seconds to respond to the customer. And in this example, a single request to the order service led to 3 downstream requests. Now, we don't know how many downstream requests were generated by those other 3 services. So this kind of configuration leads to a request and load amplification on the system. And if any of the services requires a downtime during deployment, then the entire system will be unresponsive at that particular point of time. So here's an alternate implementation that uses an event bus for inter-service communication. A typical order flow here would involve customer places an order, the order microservice creates a new record. Only this time, instead of sending requests to the other 3 services, it just broadcasts an event. Let's call it order created. And this event has additional information about the customer, the product, the price, etc. And now the payment service is listening for this event. It makes a charge on the customer's credit card and broadcasts a payment successful event. The shipping and the user service are listening for the payment successful event. And once they receive this event, they prepare the dispatch label and update the customer's loyalty points. So what do we gain and lose from this implementation? By using the event bus, we have decoupled our services. So failure of a single service does not cascade into failure of the entire system. If any of the user, payment, or shipping services goes down, orders can still be processed. Of course, this would need event playback once the service comes back online to bring the data to consistency, but we'll still be able to accept the order and tell the customer that, yes, we have received your order, and we'll process it as and when other systems come back alive. So, and the response latency of the order service is completely decoupled from other services. We can expect lower latency and improved throughput. The downsides of these design include, as we saw above, if one of the services fail, the remaining services can still fulfill a request partially. However, this leaves the system in an inconsistent state. And even if all the services are operating normally, there are these momentary occasions where the system is in an inconsistent state until all the services have processed that particular request. So, and also, in this design, instead of each service being a single point of failure, the event bus turns into a single point of failure. I personally would opt for this because now we have to basically focus on this single component in our tech stack and make sure that this is redundant to instead of focusing on keeping all the separate services redundant. So what goes into building an event bus between services? You would have heard of Apache Kafka. For the purposes of event-driven architecture, it works as a heavy-duty event bus. It's capable of processing over millions of messages per second. But then you also need a very experienced and a very probably a huge DevOps team to manage all of this. What if you have more humble requirements? I'm sure a lot of you must have already used Redis PubSub. In our case, we used a combination of Hasura and Redis PubSub for our event bus. And this is a this is how our architecture looked like. So in this setup, each service has a backing database that they access via Hasura, and each service has also subscribed to their topics or channels in Redis PubSub. And Hasura is configured to emit events for every insert, update, and delete in any table. You can always choose to select specific tables, or you can also choose for updates on specific columns. In our case, we used with almost every table. It was easier for us. And these Hasura events are then fed into an event manager service, which basically translates the database events into domain events and publishes it to Redis PubSub. So let's take an example of how this works. One of our customer updates their email ID via the user service. Hasura fires an user's table updated event with the old and new user row data. The event manager detects that the email has changed, and it now publishes a domain event, which is called email updated. And the marketing microservice, which has subscribed to email updated events, receives this information and updates the customer's email in the newsletter list. So why did we combine Hasura and Redis instead of using Redis alone? Before I answer that, I want to clarify that this is not an ideal event burst system and it violates some principles. But for our use case, it served us well. So we were transitioning from a monolith to microservices. We had a small team, and our primary goal was to not lose any event. And our secondary goal was to have complete visibility into the generation and processing of the event flow across the entire system. So we wanted to do this with minimal changes in our stack. Since we were already using Postgres and Hasura, by using Hasura's event triggers, we didn't have to go around changing code in different parts of the system. We just set up event triggers in Hasura for all the tables we were interested in, and half of our work was done. We then wrote an event manager service from scratch, which emitted domain events based on Hasura database events. You can see that Hasura persists these events in the database. So that gives us an event store without adding any new item on our tech stack. In case of failure of any service, we have the option of retrieving these old events, and we can at least manually try to rectify the errors. This is also critical from the perspective of debugging and data consistency. In case some issue happens, you'd always want to go back and look at what events were generated. You can also use Redis persistence, but then it would degrade Redis's performance. And for the complete visibility into the event flow, we just had to focus on our event manager service. We did not have to go around logging events at different points in the system. We built a dashboard just for our event manager service, and we had the complete visibility. Lastly, the reason for choosing this kind of structure where we had this centralized event generation, it's not an ideal case. It might be useful for you. It might not be. In our case, we had to sync data from Postgres into Elasticsearch and multiple third-party services. And this synchronization logic was based on updates across various tables. So for this, it was very convenient for us to tap into any changes in the database and trigger an appropriate HTTP request to whichever third-party service we are syncing the data to. So taking all this into account, a combination of Hasura and Redis was a better choice for us. Now, before I end the presentation, one tip for anyone using the Hasura event triggers, in case you're not using this, when you make a request to Hasura, always send a request ID using a header prefixed with X Hasura. Hasura will send the same header and its value back to you in the event payload. Now, this helps you to correlate the event chains and implement tracing across all services. It is very critical when you're debugging event flows. Thank you, everyone. I hope you found some useful ideas about using Hasura in your system. You can reach out to me on my email at chi@krafteer.com. Before I leave, a small plug. We are currently working on a product Deploy Bob to make self-hosting and deployment simple and easy. If you're looking to self-host Hasura, Postgres, or any other stack, you should check us out at deploybob.com. We are in private beta right now, and we are rolling out invites fortnightly. Thank you.